Hi everyone, so welcome back. अब कम बैक करते हैं अपने मेन टॉपिक पे विच इज़ द बूलियन अलजेब्रा. सो बूलियन अलजेब्रा में हमारा क्या था, एक बार रिव्यू करते हैं. बूलियन अलजेब्रा में सिर्फ दो सिंबल्स होते थे विच इज़ 0, 1, राइट, विच इज़ this one is boolean 1 and this is boolean 0, which is high, this is low, right? You remember about and, or, and not operations, right, which is also called as complement. If there is a variable, then its complement will be, if it is 0 then it will be 1, if 1 then 0. For or, either of one of them should be 1, right? If both are 0 then it will be 0, like this. And in and, both should be 1. If any of them will be 0 then it will be 0, right? So this thing is clear. These were the operations. Now we had also discussed about how to create circuit using switches to implement an AND operation. For example, AND function, like for example for 1, let me create a circuit. Okay, so this one will glow if both of them will be 1, and here if only one of them is 1, right? So this was a circuit for and this is for the OR. Next, you remember the NOT gate that we have discussed? So complementation is called inversion, and it is a electronic gate, so which forms the inverse of x, right? That's why it is also called as inverter. इसे इन्वर्टर भी कहते हैं. तो ये कॉम्प्लीमेंट बनाएगा, right? तो symbolically we represent it like this. If the input is low voltage, then the output will be high voltage, and if the input will be high voltage, then the output will be low voltage. Similarly, for AND gate, what was the symbol? Like this. For OR gate, what was the symbol? Like this, right? These things we already know. Now see some more standard operation. So now, so far we have seen these operations, right? And, or, not, right? But there are some more. First of all, we'll talk about NAND. What is NAND? The name itself is telling you. What is it? Negation of, not of, and. So NAND gate means not of and. Okay, what is the symbol of this? An upward arrow. Okay, something like this. So first you do and then you do negation or the complement. Now what will be the NOR operation? It means not of OR. So first you do OR, then you do NOT, and its symbol is downward arrow. Like, so what will be the truth table? So for example, if you have two variables, first create AND, then what will be NAND? And complement. Then OR, and the NOR will be OR complement. Right, and the combinations will be 0, 1, 0, 1. Right? Only two possible values. So four possible combinations. But these four combinations we write normally in the order of their binary number. इसीलिए मान लीजिए this is the binary number 0. So what will be the truth table of AB? You know AB, it will be 1 if both are 1, else it will be 0. Right? Now complement of AB. So complement of 0, 1, 0, 1, 0, 1 and 1 is 0. So this is your NAND. This will be the truth table of OR. Complement will be 1, 0, 0, 0. So this will be your NOR. So this is very simple, right? This is the idea of NAND or NOR. Now why do we call them universal gates? These are called universal gates. NAND and NOR are called universal gates. But why? This we will see later on. For NAND operation, we have a digital circuit. Operation and digital circuit. Implementing that operation. Right? If your operation is NAND which is complement of AND. So complement of AND. First you'll make AND, and then like this, and then this bubble over here. This bubble means not. So and not, which is NAND. So for a NAND operation, this is the digital circuit. First you do AND, then you do NOT. First you'll do AND A comma B, and then you'll do the complement. That's why this is the symbol. So for OR, so first you'll do OR. So this circuit will do OR, right? Then you'll do NOT. Then this is your NOR operation digital circuit. This is called NAND gate, and this is called NOR gate. Not of AND, not of OR. So this operation, next operation, is exclusive OR. The name itself telling you, what is it telling you? Exclusively one of them must be true. Right? Okay. For example, if we have these two symbols, what is the symbol? This is the symbol. Now this is your XOR. Again, there are four possibilities. Can I say exclusively one of them is 1? Yes. Here also exclusive one of them is 1. Can I say here exclusively one of them is 1? You know exclusive news. For example, analogy, exclusive interview. You would have heard these words. So here there are no exclusive one. So here there will be 0. So XOR means exclusively one of them should be 1. So this is the whole exclusive OR operation. Is this clear to everyone? So we can say A exclusive B is 1 if and only A and B are different. When they are different, then you'll get 1. They are different, you'll get 1. When they are different, you'll get 0. They are different, you'll get 0. This is important. It will be only be 1 when they will be not equal to 1. They will be not equal. So here this is A, this is B, this is A XOR B, 0 0 0 1 1 0 1 1 0 1 1 0. This is 1 if and only if A equal to 0, B equals to 1, or A equal to 1, B equal to 0. So A exclusive OR is B either this or this would be happening. Now we'll follow a convention. If I want to say something is 0, then I'll write like this. If I want to say something is 1, then I'll write like this. So this is the convention. We'll understand this convention later on when we'll move further in the syllabus. If you want to write A equals to 0, you write A bar. Whenever you want to write a equals to 1, you write a. We'll learn later, will be explained later. This is the convention while writing expression. This convention will save a lot of time. A equals to 0 means a bar, and a equals to 1 means simply a. If we want to write a bar equals to 0, then what should we write? We should write a. Why? Because alpha, if alpha equals to 0, then if it's alpha dash, and if it's alpha equals to 1, then alpha, right? For example, for this ex- expression, if and only if this one, is this clear to you? A exclusive B equals to 1 if and only if either this will happen or this will happen. Now we can say A exclusive B is equal to A equals to 0 equals to A bar B or A B bar. Is this clear now? Is this thing very clear? Or over here, and then A B bar like this. Now let us see our next operation, XNOR. Now name itself tell you what this is, XNOR, which is complement of XOR. The name itself is telling you. What is the symbol? This is the symbol for this operation. Either you can use this symbol or you can use this symbol. Right? We'll understand this thing also. So it is the complement of XNOR. So this is another operation. Now tell what will be XOR and what will be XNOR. 00011011. This will be 1 when both will be different, otherwise 0. Complement will be 1001. Right? This is your XNOR. So either you can use this symbol or you can use this symbol. Both are fine. Now let me tell you why people are using this symbol. Tell me one thing. This XNOR is 1 if and only if both are same. Both are same. Look at this. Both are same. If and only if A equal to B. That is why some people use this symbol. If and only if both are 1. So this will happen. So remember two things. XOR will be 1 if both are not equal, and XNOR will be 1 if both are equal. So they are complement of each other. So this is the idea. So these are the complement of each other. This is the entire idea. Now understand which digital circuit will implement these operations. For example, this operation you have XOR. Which digital circuit will implement this operation? The digital circuit name is XOR gate. XOR gate. What is the symbol? This is like an OR, but exclusive OR. So one more layer you have. OR, first OR, but this is exclusive, so we put one more layer like this. So this symbol we use. Is this clear? So this is the symbol for XOR gate. Okay. Similarly for XNOR, this means like this. This is again very simple. This is the complement of XOR. This is your XOR. Complement will be XNOR. So this will be your XNOR. Very simple. Again, this bubble you understand, this means not. So these things are very simple. Now how to write equation for XNOR? See, 0001 1011. So this is one only and only if A equals to 0, B equals to 0, or A equals to 1, B equals to 1. So very simple. Either this will happen or this would happen. So this XNOR will be equal to, how do we write this? We write this A bar plus B bar plus, and how do we write this? A B. Is this clear? This is how we write the equation. Understood? Whatever I give you, you can write the equation. For example, AB and some FFs there. 00011011, right? And let's take it 1011. Then how will you write it? Right. Right. Equation for F. So what is F? F is 1 here, here, here. When F is here. So when A0, B0 or AB0 or AB. So very simply you can write the equation. Just focus on once and you can write the equation very simply. Here A1 B0, which means A B bar. Here first of all A0 B0, so A bar B bar. Then A1 B0 A B bar. Then A1 B1 AB. Right? Now we are going to see standard form of truth table. See, truth table doesn't have any standard form, right? Any form. For example, if we have this, does it have any form? Is this correct truth table? This is correct. There is no problem because this truth table is correct. You cannot notice that for this combination value will be 0 and will be 1 and will be 0 and will be 0. Right? This truth table is correct, but there is no problem with this truth table. What is the standard form of truth table? So this truth table we write in the form of their binary number. Like this we write 00011011. This we say this is raw number. So we write these combination in the order of their binary number. So 0, 1, 2, 3. So this is your standard form of the truth table. So this is the idea behind it. So truth table is same. Both are same. But this is the standard form, standard representation. So if I have three variable a plus b dot c, this is the expression e a b c. What is the standard form? 0, 1, 2, 3, 4, 5, 6, 7, 8. See, like this 1, 2, 3, 4, 5, 6, 7, 8. What will be E for this combination? When C is 0, then E will be what? E will be 0 because when C is 0, you have AND. E will be 0. So, here E will be 0. Here E will be. So, in remaining, when C is 1, then what will be 1? Then what will be E? This is the observation that you can make. When C equals to 0, then E equals to 0. Right? And when C equals to 1, basically E equals to A plus B. Because C is already 1. If C is 1, then it will only depend on A plus B. So this is the idea. So here, this will be 0, 0. This one will be 1. This one will be 1. And this one will be 1. So this is your truth table for expression E. Is this clear? So if you have 3 input AND gate, you can create that also, right? In the market, if you go and purchase AND gate, you'll not get 3 input. You can create 3 input, but you'll not get. For example, this is your AND gate, 2 input AND gate. This will give you AB. And this is your 3 input AND gate. It will give you ABC. If you go to market, will you find this? If you want, you can create this. But in the market, you will find only standard sizes. It is also very hard to find. Because what they will do, when they'll create the gate, they'll create 4 ring. They will manufacture 4 input. While they'll manufacture 4 input, so that if someone comes 4 input, they'll give this one. They will come. If someone comes with 2 input, they'll give this. If you want two input, then what you should do? They should be connected to 1. Why? क्यों? ताकि ये AND ऑपरेशन को अफेक्ट ना करे, right? So if you have 3 input AND gate, 4 input AND gate, that is how you can do it. So that is the standard form of our truth table, which we have discussed earlier over here. The row number in the order of the binary number, we write the combination and then the results. So you can see this 3 input AND and OR operation. So 1 when all are 1, 0 when all are 0. Okay, so this is what we have seen. Now we are going to understand what is literal. So look at this statement. Each appearance of a variable or its complement in an expression will be referred to as its literal. Understand, if you have variable a, then what is literal? Literal is basically a comma a bar. Each appearance of variable or its complement in an expression is referred as its. For example, in this expression, here you have only 3 variables, but there are 10 literals, right? So now, in this expression, how many variable and how many literal? Variable you only have 1, but how many literals you have? You have 3 literals. Is this clear? Yes. Number of appearance we are talking about. So you have to focus on each appearance. You have 3 literals and 1 variable. So this is the entire idea. So if I give you a plus a bar plus ab, the number of variables, you have 2 variables. Literals you have 4. Right? So that's all for this lecture. We'll meet in the next lecture.